So today I'm going to sketch the proof of universal optimality. So namely this. So recall that we're trying to show that E8 and the Leech lattice are universally optimal. And even stronger than that, that they're sharp for the linear programming bounds. That they're sharp for the linear programming bounds for energy minimization. For completely monotonic functions of squared distance. So that's what. So universally monotonic, universally optimal says that they optimize every completely monotonic function of squared distance, but in fact we're even going to show something stronger, that they're sharp for the LP bounds. So that's the theorem. Let me just state it so that that's the goal. Universally optimal. Okay. So if you're looking at completely monotonic functions of squared distance, the prototype is a Gaussian. So given f of r, for example, Gaussian e to the minus pi c r squared, what do we need to do? We need to produce h of x, a Schwartz function, let's say, of course this is a Schwartz function, and without loss of generality, it's radial, so it's just also a function of just the distance from the origin, such that h of x is less than or equal to f of x. So I might have stated this with an f of x squared last time. So there are sometimes competing notations. I think in the original paper that Henry Cohn and I wrote, I think we were saying that f is a completely monotonic function, and we are thinking of the f of x squared. But anyway, I mean, we're just going to think of f as as a Gaussian, for instance. So h interpolates, h is going to lie below f, and to have a sharp bound, you need equality at all the vector lengths that you see in either the E8 lattice or the Leech lattice. So for n equals 1, 2, dot, 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 for 8 dimensions, and n equals 2, 3, dot, 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 for 24D. Okay, so that's what we need to do. Given h, given f, we need to produce h such that this is satisfied with equality everywhere at these distances, and you also need that h hat Fourier transform is non-negative. Okay, so if you could do that, then you stand a chance, and in fact, you would also need, so let me just say, and h hat of x, h hat is 0 at x equals, again, these distances, these same distances for a sharp bound. So these are all the things that you need. So fairly severe list of conditions that you need to produce to get a sharp bound for the linear programming bounds of potential energy. Okay, so so let me sort of recall what happened in the sphere packing case. So the sphere packing problem produced functions let's call them A of x and B of x. So there are plus and minus eigenfunctions such that A is a +1 eigenfunction and B is a -1 eigenfunction for the Fourier transform, and such that A of sorry the A at all the square roots of the even integers is 0. But if you look at the sorry, for all m, and A prime the square root of m is 0 except at, so remember the function had a single root at square root of 2, so except at the first one is going to be 0, and the first one is not going to be 0. And so we can normalize it to be just 1, and similarly B of the square root of 2m is 0, and B prime square root of 2m is delta m1. Okay, so plus eigenfunction minus eigenfunction satisfying these properties, then you can take, we could take, so remember the Fourier transform has to be has to actually have a double 0, not just a single 0. So you need to take a linear combination. So you take f equals, let's say, a plus b, and f hat would be a minus b because of the Fourier transform. And you see that, you know, f hat has double zeros everywhere. So f hat square root of 2m is 0 for all m. Okay, that's the sort of thing we did there. So one, oh, for the Fourier transform, this is the Fourier transform, and A is a +1 eigenfunction. So here, one key idea is to generalize these functions to a family of functions, to find an entire sequence of functions which do something similar, except sort of one, you'll have one for every n, not just n equals 1, and you use that to interpolate. So roughly, here's what we're trying to do. You're given some Gaussian, you know, this is f, and you're trying to interpolate it. So whatever h that you need to come up with has to lie below it and has to look like that. This is h at all, you know, square root 2, square root 4, etc. has to touch. On the other hand, h hat has to be, whatever h hat is, it has to be 0 at all those places. H hat. That's the kind of thing you're looking for. So you're trying to essentially do Hermite interpolation at an infinite sequence of points. Okay, that's what this is going to be. Except you also have some conditions of Fourier transform. And so we're going to call this Fourier interpolation. So let me define what we want. So, so one key new idea is to generalize these functions a and b. So you find a sequence of functions which we'll call C plus minus comma n x. So they'll depend on an index n, and let's say going from 1 to dot, satisfying the obvious extension of that property. So C plus minus n of square root of 2m is always 0, and the derivative C plus minus n prime at the square root of. So these are all going to be radial Schwartz functions. So let me just say sort of radial Schwartz functions. So I can write things like c plus minus prime of square root of 2n. It's radial, so you're just looking at any point which has that norm, that length. So this is equal to delta mn. Okay. So this, in some sense, you can think of it as interpolating derivatives. Okay. And similarly, you can, if you wanted to interpolate values, you could find a sequence of functions. You do need to interpolate values as well because you need to match the value of f. So, and also d plus minus nx n equals 1 to dot. This is all in the 8-dimensional case. In the 24-dimensional case, you skip the first one. But anyway, satisfying d plus minus n square root 2m is delta mn, and d prime is 0. Okay, for all this is for all m. Okay, so it has to satisfy. We're looking for functions which do that, and then if you could find such functions, then we can use them for interpolation. So okay, then use them for interpolation. So for example, if f of x is a Fourier plus 1 eigenfunction and a Schwartz function, then you can write then you can try to write the auxiliary function for that f. You know that it has to match the values of f at all those points, so you can write it as sum over n d plus n of x times this coefficient, which is just a number f of square root of 2 to n, plus sum of over n of c plus n of x f prime at the square root of 2n. So yeah, so this kind of function would help you interpolate. Let's see. It would have the same values as f, as well as the same derivatives at f at all those places. Okay. So more generally, right. Actually, before I go there, let me see something. Yeah, this is a little. This is not quite what I want. Sorry. Unfortunately, this is going to satisfy this part, but it's not going to satisfy the Fourier transform. If you take the Fourier transform, you just get. Oh, actually, yeah. Sorry, this is fine. In this case, you cannot have f being this and f hat sort of vanishing. If you just want, yeah, I mean, in this case, if you just wanted to interpolate f of x at all these points, you would, by plus 1 eigenfunctions, you would do it like this. I'm not making any promises about h hat at, because h is an eigenfunction plus 1 eigenfunction. You just, you cannot make it 0 at all those points. That's just not physically possible. But we can, once you extend that line of thought, I'll sort of write down the more general version. Okay, so then let me just say, then in that setup, assuming convergence, etc., which for the moment let me wave my hands, but of course you have to check everything very carefully. It's easy to see that h of root 2m equals f of the square root of 2m for all m, and you know, so yeah, if you look at one particular square root of 2m, what happens? First of all, you know that c is 0 at all these square root of 2m, so all of these functions vanish. So you can ignore every term here, and here it's going to pick out n equals m because all the rest of them vanish. Okay, so you see that you know, it matches the values, and similarly it matches the derivatives. So in the sum over d plus n, f is a +1, yeah, radial Schwartz eigenfunction. Nothing more, yeah. And h prime square root 2m equals f prime square root 2m. Again, by the same reasoning. And yeah, in this situation, what's going to happen is, right, so in this situation, it will transpire that h equals f. So the point is, you can actually recover the entire function by using its values at this infinite set of places. If it's a Fourier eigenfunction, you can get the whole thing out. And we're going to prove that such functions exist at least in 8 and 24 dimensions. Conjecturally, they may exist in other dimensions. We don't know. But in particular, any radial Schwartz function you will be able to write in terms of these basis functions if you just know all their values at all the square roots of even integers. Okay. So the key idea is the notion of Fourier interpolation, and similarly for -1, you have a sequence of functions which does, you know, the -1 will do this. Cn minus is going to do the same thing. What does this mean? So let me, before I say what that exactly means, let me just say, so after some algebra, you can change to a basis which doesn't necessarily have eigenfunctions, but sort of arbitrary an, bn, an tilde, and bn tilde, which will encode the values of the function and its Fourier transform. So here's what we desire. So want, yeah. Oh, an tilde and bn tilde. Yeah. So here's what we want. So let me just say specifically. So there exist. Here's what we propose must happen. So there exist radial Schwartz functions. An of x, bn of x, an tilde of x, and bn tilde of x, such that, so for n, at least n0 is 1 for 8 dimensions and 2 for 24 dimensions. I'll say that again, such that for any radial Schwartz function f of x, we have, let me write it up here. We have f of x equals n greater than equal to n0 of f of square root 2n an of x plus this whole sum. Yeah, let me just f prime of the square root of 2n bn of x plus f hat at the square root of 2n an tilde of x plus f prime hat, sorry, f hat prime square root 2n bn tilde of x. Okay, so this is true as an identity of Schwartz functions. Okay, so these two for here, n0 equals 1 for dimension 8 and n0 equals 2 for dimension 24. Okay, so this is actually a theorem that we proved that there exist such functions, and this is the Fourier interpolation theorem. That's the key to the whole affair. These an, bn, etc. are called the basis functions. It's a theorem. That Fourier interpolation holds. For 8 and 24 dimensions with the above parameters. And in fact, the basis functions are unique. Are uniquely determined. And it follows that an tilde is actually the Fourier transform of an, and bn tilde is bn also the Fourier transform of bn. By uniqueness, it follows these things hold. Right. How does this help us for interpolation? So let's write down. Once we have the Fourier interpolation theorem, then we can write down auxiliary functions for every f. Sorry? These basis functions which satisfy these, given these, which satisfy this property, they're unique. Yeah. There's only one set of basis functions which does that. So that such that for every radial Schwartz function, right, it's going to have. So in particular, if you look at an, right, and you plug in an here, you see that an is the sum of this stuff, but an already appears here. So you know that an has to have, you know, the only, so you get that an of the square root of 2m is delta mn, and so on. I mean, you get that its derivative is 0, you get the Fourier transform is 0, and the derivative of its Fourier transform is 0. That's quite a lot of conditions. It's enough to pin it down. So all these functions, they're unique. At least in these dimensions, we can prove something. Okay, so once we have Fourier interpolation, it is easy to see that if you're given your function, the auxiliary function, there's only one thing that it could be. The only auxiliary h of x that could give a sharp bound is the following thing. So let's just think about it for a second. Whatever h of x is, you know all its values and all its derivatives, right? All its values are the same as the values of the f of at the square root of 2n, and you know its derivatives also have to agree. Its Fourier transform is 0, and its derivative of Fourier transform is 0. So all this stuff vanishes. You just get that if f is of that form, I mean, which it is, then h must be this thing. So h of x has to be, there's no choice, n greater than or equal to n0 of f of the square root of 2n, an of x plus f prime of square root of 2n, bn of x. There's no choice. Okay, so that's the auxiliary function, and it will follow from the interpolation theorem that it interpolates correctly, so it gives you the right values and derivatives. The key thing that you need to check is you need to check two things. You need to check that h of x is less than or equal to f of x, and you need to check that h hat is non-negative. And that's actually where most of the real work is. But I mean, that's quite a lot of, so that's something that we had to do a tremendous amount of computer algebra to verify. But I'll say a few words about that later. Okay, so since, let me just say, this h has h hat and h hat prime vanishing at square root 2n, n greater than or equal to n0. And this is just what I just said. So h and h prime agreeing with f and f prime respectively at square root 2n, n greater than n0. This is the thing. This is by the Fourier interpolation theorem. Okay, so that's the, just wrote down the justification. So I want to describe, so the paper in which we prove all these things is kind of long, is 90-something pages. So I'm not going to go through all of the paper, obviously, but it's, as math papers, most math papers are anti-pedagogical. They don't really tell you how, you arrived at the result, right? I mean, it's not really a fount of intuition. I just want to say something about how you arrive at these functions, which is how we actually solve the problem first. So first thing you do is these functions, a and b n, they all or rather they're eigenfunction versions. They generalize what we did for sphere packing. So you can actually compute all of them one by one. You see a pattern, and you can make a generating function. And it turns out the generating function is the key thing that you need to show some functional equation holds for it, which you do. And then finally, you need to show some equality in two variables, inequality holds for it in two variables, which is also, so that's how the sort of paper is laid out. But I want to give a little bit of sort of, intuition. So I'll let's describe how we arrived at these functions, these basis functions. And then I'll sketch how one actually proves the Fourier interpolation theorem, and sort of then go on to, then universal optimality, how that's proved. I mean, that's also non-trivial. Even when you have the Fourier interpolation theorem, you still need to prove the serious inequalities, and it's not trivial at all. Okay. So in the sphere packing case, you can concretely compute the basis functions, the eigenfunction that we had, by making an appropriate ansatz, right? We made an ansatz that it was, -4 sine squared pi r squared over 2 times this integral of this quasi-modular, weakly modular form, and then figuring out what transformation properties it implied for that function of, that complex function. Turns out implied that it has to be a modular form of some sort, and then solve. So a similar thing that you do here. So make a similar ansatz. In this case. So let's say we're doing +1 eigenfunctions. So you assume that Cn plus is sine squared pi r squared over 2 times, I have a constant somewhere, but anyway, some constant, doesn't matter, an integral from 0 to infinity of e to the pi I r squared z times phi 0 of minus 1 over z squared dz. Okay. So we make exact same answers. This is the E8 case for the moment. Then it turns out that what you need is that phi 0 has, make sure this is correct. Oh yeah, sorry. I think I want dn. Let's do the values first. Okay, so the derivatives are slightly different. So in the values, so phi 0 has depth not 2 but 1. So it doesn't have e2 squared showing up. It has just e2 showing up. So depth 1. In the derivative case, c plus n, you're going to get depth 2. Okay, but here you have depth 1. You have a denominator of some power of delta. And you're going to get z squared phi 0 minus 1 over z. You want, yeah, here's the key thing. So when you do the Q expansion near infinity, you get that this must look like z e to the 2 pi I and z plus O of z as z goes to infinity. This is really a plus. I hope I did this right. Oh, maybe this is a minus squared pi ar squared. Here you're going to get, let me just check. So r squared minus 2n. Yeah, I think you want I think, yeah, maybe you want a minus. Right, these things, yeah. I mean, e to the 2 pi I n z, that goes to 0 as z goes to infinity, right? I mean, z goes to I infinity. This you're going to get, if z is it, you're going to get 2 pi, by itself you get minus 2 pi t. And that already goes to 0, so it doesn't make sense to say that's O of z, because already everything is O of z. So this is, sorry. So you have a pole, in other words. So in other words, if z is it, this sort of looks like, again, I don't care too much about the constants. It's going to look like t times e to the 2 pi nt plus O of t. Okay. And the point here is, when you do the Laplace transform of this thing, you're going to get r squared minus 2n in the denominator. One single pole, r squared minus 2n. And so what that's, sorry, that's what you would get if you didn't have the t here. But since you have the t here, you get r squared minus 2n squared. And so what that does is gets rid of the entire double pole at square root of 2n. So that means whatever your value is at square root of 2n, it's going to be non-zero. Whereas all the other square root of 2m's, it's going to have a double pole. So it satisfies the template that you want for your function d plus of n. Your question, Ravi? Oh, okay. So that's the key property that you want, and you see that this imposes, you're going to get some space of quasi-modular forms when you do this. So I think here you get, the nth, namely, I think you get the nth power of delta in the denominator, or I think you get delta to the 2n if dimension is 24. And this is the case when dimension is 8. So you get some space of modular forms, and you impose a bunch of conditions, namely it doesn't have any poles between here and sort of O of z, right? And the constant constant part of the Q expansion. So that cuts down the space, and you end up getting one single form up to scaling. Okay, so you can actually solve for this form. So we have some sequence of, let me say, Yeah, what does this imply? So we have some space of quasi-modular forms, weakly modular, which just means there are deltas in the denominator, weakly modular forms. And we impose linear conditions on the Q expansion. Sorry? That's right, yeah. So I should say this is dependent on n, right. This is, I didn't specify that, but every n has its own phi 0. So there's some space of quasi-modular forms that you get by considering depth 1 and delta to the n denominator. And you impose a whole bunch of linear conditions on the Q expansion, cuts it down to one-dimensional space. So cuts it down. One-dimensional. And then you can just solve for phi 0, and that its integral is going to give dn plus. And similarly, for Cn plus, dn minus, and yeah, actually, let me just say what happens for Cn plus first. So for Cn plus, you get depth 2 and the same denominators. Okay. And here you want z squared sort of, for the Cn case, you want z squared phi 0. This is a different phi 0, minus 1 over z. That should just look like e to the 2 pi minus 2 pi I n z plus O z. Because there's no z in front. And therefore, that interpolates, it converts the double root to a single root by having a simple pole there. Right. So that's what you get for the plus eigenfunctions. For the negative eigenfunctions, in the 8-dimensional case, it's enough to use genuine, not quasi-modular, but weakly modular forms for gamma, but this time for gamma of 2, just like in the sphere packing case, we had these u, v, and w. Again, you're going to have denominators delta to the n for when you look at the sort of Cn minus or dn minus to nth one, and for there's one twist in the 24-dimensional case. We need one extra. Just like you need E2 here, you need an extra twist. You need log of lambda. This is not really a modular form where lambda is v over u. So remember, v and u were these modular forms of weight 2 for gamma of 2. And so this is the Haupt module for gamma of 2. Okay, so I mean it's the analog of j for gamma of 2. That's what lambda is, and it's sort of an analog. I mean, you can think of it as an integral of a modular form. Log lambda is an integral of modular form. So it's sort of, if you take derivatives, you get E2. If you take an integral, which you seem to require in this case, you would get log lambda. Because that's required. I won't sort of go into all the details for how it shows up. Anyway, so now, so you can compute all of these, and we did. Now that we have all of these. So this is a fair amount of work. You have to postulate, a certain space, and you figure out what transformation properties you need, and so on and so forth. And finally, you get it all, the sort of, at least the first few of the sequence of forms. You can make a generating function. I mean, you get one for every n, so you can multiply it by a different q to the n. You can multiply by x to the n, and you can sum over. And what you get is a two-variable modular form, okay? Because you already have q of z here, and you can think of the other one as a tau, q of tau. So you get a two-variable kernel, and turns out to be a quasi-modular form in two variables, tau and z. So we just call some kernel. Okay, they're different from the positive definite kernels. But okay, so that's roughly how you get at these functions, and you combine them. When you actually want to prove the Fourier interpolation formula, it turns out it's better to start with that kernel, which you've sort of guessed the form of, and then prove that it has various pleasant properties. So let's go back to the general framework, where it's a little easier to prove things. So, so remember that cone of completely monotonic functions is spanned by the Gaussians. So it's enough to show the Fourier interpolation formula for, well, actually, this is a little stronger. Yeah, I shouldn't say. So let me just say that the Gaussians actually span Schwartz functions. Yeah, let me not say. So let me just say Schwartz functions. Because the Fourier interpolation formula doesn't care whether you have a completely monotonic function or not. It's applicable to any Schwartz function. So in fact, if you're not looking at the cone, you're just looking at the linear space they span all the Schwartz functions. That's a lemma in our paper. It's something well known. So it's enough to show the Fourier interpolation formula for f of r being e to the pi I tau r squared, okay, where tau is imaginary. So if you could show it for all such Gaussians, then you would show it for all Schwartz functions. Okay, so then what does the Fourier interpolation formula say? So there it says that e to the pi I tau r squared, that must equal some, right? I mean, you can write down explicitly what you need. E to the 2 pi I tau. This is the f at the square root of 2n, an of x plus 2 pi I square root 2n, 2 pi I tau square root of 2n times e to the 2 pi I n tau bn of x plus similar things involving a n tilde and b n tilde, okay? Where now you have to Fourier transform the function, and you get a minus 1 over tau, and you get appropriate things. Okay, so this is the derivative of this thing is the derivative of e to the pi I tau squared at square root of 2n. Okay, so it's saying that this must be satisfied, and also while we are here, let me just say, what does what does the universal optimality say? So for universal optimality, we need, yeah, let me just say, this is the whole Gaussian, it has to be this thing. On the other hand, the auxiliary function, while we're here, let me just say what the auxiliary function looks like. That's just the first line of this thing. Okay, so that's just n greater than equal to n 0, e to the 2 pi I n tau a n of x plus 2 pi I tau square root 2n e to the 2 pi I n tau d n of x. Okay, so this is what we're going to call. We're going to call this thing f of tau comma x. Okay, this auxiliary function is a function of tau and x is f of tau x, and you can write, I mean, you can write the whole function, the whole of this thing in terms of f of tau x and f of minus 1 over tau and x. It's straightforward. So you get a condition that that sum must equal the Gaussian, but in any case, for universal optimality, you need that this f of ix, this f of tau x needs to satisfy that f of icx less than or equal to e to the minus c pi x squared. I mean, this inequality has to hold, and also that f hat of icx, where hat is in the x variable, is greater than or equal to 0 for all x. So this hat is in x variable. Okay, those two conditions for universal optimality, for that one you need. So it turns out that the following is true. You make this ansatz that fd, d is the dimension 8 or 24 of tau x is the following thing: e pi I tau x squared plus 4 sine squared pi r squared over 2. So the point is, each of those cn's and those an's and bn's were integrals of this form, sine squared pi r squared over 2 times something. F itself is a linear combination of them, so it's going to be an integral, but there's some amount of switching the sum and taking out poles, and that's why you get this extra term, okay, from 0 to infinity of the generating function of those things, which is the kernel tau it e to the minus pi x squared t dt. Okay, that's the ansatz, and you can then show that this actually works, where k of z tau z is exactly the kernel. Sorry? Yeah, f hat of ic comma x. Yeah, hat is in the x variable, right? The Fourier transform. So where this thing is exactly the kernel, we computed an expression that's quasi-modular in tau as well as z. And then the desired inequalities, you can transfer them. You want to show these inequalities for f, you can actually transfer that to the kernel. Qualities will be obtained by showing that the integrand is non-negative. So namely that kd of I alpha it, that's always non-negative for alpha and t greater than 0. Okay, so I mean, this is sort of very, I'm not going through all the details, which take quite a bit of work, but let me just say it requires a little bit more than this for d equals 24. For d equals 24, need a little extra because of convergence issues for the integral. of that integral, and so it has to be analytically continuous, and so you need a little extra work to show that. You need a little more than just this to see these two conditions hold. Okay, so that's a tremendous amount of work that you have to do. I mean, once you have this kernel, you have to do a lot of computer work to actually show that it's positive. Anyhow, we can do that. So prove by extensive computer calculations. I mean, we did try by hand proofs, but nobody could come up with something really good. Okay, so to prove, once you make that ansatz, I mean, once you prove this is all once you prove the Fourier interpolation formula. To prove it, you prove Fi. We first reduce it to showing that this generating function f of tau x, as defined here, that satisfies the following two things. So if you hit it by the Hecke operator in tau of weight d over 2, then that Hecke operator is t minus 1 squared, so that's 0. So it's annihilated by, this is the first function equation. So in other words, all this means is that f of tau plus 2x minus 2f of tau plus 1x plus f of tau x is 0. Okay, that's what that is saying. And then similarly, the other functional equation satisfies f hit by s t minus 1 squared. That's 0. Okay, so you can show that these two imply the functional equation. Okay, and equivalently, oh, sorry, this is not 0. This is not 0. This is the same thing as when you apply it to the Gaussian, pi I x squared tau hit by s t minus 1 squared tau d over 2. Okay, so you have to solve this functional equation. I mean, you have to show that it satisfies this. So equivalently, for k, if f is defined as integral above, then k satisfies the functional equation. Then you need k hit by, so k of tau z hit by these Hecke operators is actually 0. Okay, so t minus 1 squared is 0, and k tau z hit by s t minus 1 squared is 0. That's a functional equation that quasi-modular form in two variables has to satisfy. So it turns out if it satisfies these functional equations with respect to tau, then automatically it will satisfy some with respect to z. So let me say some words. So furthermore, k must satisfy some growth bounds in order to have a reasonable integral, and also some residue formulas at tau and SL2Z translate of z. So that must hold, and these in turn imply that f also satisfies some functional equations in the z variable. So I'm sort of indicating, once we know what we're looking for, once we make this ansatz, there's enough information to independently get the kernel even if we hadn't computed it term by term over there. Okay, so this is sort of information which tells you that it satisfies so many functional equations in tau and z variables, so you can basically figure out how to get at this kernel. And that's how the paper sort of develops it. But of course, the way we saw that it has to be of this form is sort of first computing it and then checking. Solving these, right? Solving these functional equations involves some analysis in the group algebra. The advantage of doing it this way is not just that it's sort of theoretically cleaner, but also that it essentially gives you that there's a unique way to do it, to find out this kernel. Okay, I mean, of course, you could compute it, and you know that intuitively you know that there's only one answer, but this actually shows you by looking at the group algebra representations that there's only one answer. Representations. So again, I'm glossing over lots and lots of stuff in the paper, but it's kind of impossible to go through all of it. So I'm sort of indicating the main features in the 8 and 24 dimensional cases. One can write down explicit kernels. So it's possible that these exist in other dimensions. We don't make a conjecture either way, but we certainly haven't tried to compute in other dimensions where similar kernels exist. Okay, so I have plenty of time. So the last thing I'm going to do, and then I think I guess we'll end a little early, is I'm going to give you the description of the 8-dimensional kernel. Okay, so completely explicitly I'll describe it. So let consider these three quasi-modular forms. So phi 2 of tau be tau e2 of tau squared minus 6i over pi e2 of tau. Phi 0 of tau be tau e2 of tau minus 3i over pi, and phi minus 2 of tau be tau. Okay. Okay, then on the z side, right, phi 2 tilde of z be z e2 of z minus 6i over pi squared. Phi 0 tilde of z be z squared e2 of z minus 6iz over pi. Phi minus 2 tilde of z be z squared. Okay, so these expressions. Then you let consider this diagonal matrix pi 6 4 2 of tau be diagonal matrix e6 of tau, e4 of tau, e14 of tau over delta of tau. Okay, zeros everywhere else. Pi. So 6 4 2 are, by the way, all these I guess encode some kind of, the subscripts are supposed to encode some kind of weight basically. So 6 is the weight of e6 and 4, etc. Pi 12 10 8 of z be delta of z e10 of z e8 of z. Okay, let's keep going. Okay, then we define a matrix epsilon of, this is for the plus kernel, epsilon 8 of tau z is the following matrix. So it's pi 642. It's that pi 642 of tau times a matrix which I'll write down, slightly bigger, and then divided by something pi 12, 10, 8 of z. And the matrix is j sub tau z 0, 1 minus 2 j sub tau z minus 2, 0, 1, 0, 0 divided by 36 over pi squared I delta of z j of tau z, where j tau z is j of tau minus j of z. Okay. So this gives you some matrix, and K8. So the plus kernel in the 8-dimensional case is the following thing. It's phi minus 2 of tau, phi 0 of tau is this row vector, phi 2 of tau multiplying this matrix epsilon 8 plus of tau z, and multiplying the column vector phi tilde minus 2 of z, phi 0 tilde of z, and phi tilde 2 of z. Okay. So you can write down everything completely explicitly. I mean, it's pretty complicated, but and you can, from these descriptions, you can compute residues and growth bounds, etc. Okay, so this is the plus part of the kernel in 8 dimensions, and so that means it satisfies if you hit it by the Heck operator 1 plus s in tau, and you get 0, because that satisfies that additional identity in addition to those two that are hit by st minus 1 squared and t minus 1 squared is 0, because one. So similarly there is a minus part K8 minus, and then the kernel itself is half of the sum. K8 is 1/2 K8 plus K8 minus. Okay, so we finished early. That's it. Then you can have to, of course, you have to do all sorts of work to show everything, but that's sort of all I wanted to say. Yeah, exactly. So what happens is the functional, if you look at the solutions of functional equations, if you look at appropriate modular forms in tau which are killed by these things, it turns out that space is essentially generated by these things. That's why the row vector shows up. And similarly, the functional equation on the right is generated by these things. And so that's why those show up. And then there's something in the middle that you have to sort of basically follows from all the residue properties, when tau is a SL2Z translate of Z and so on. So the way we prove it so yeah, I mean, you know that it has to have this form. The question is, what matrix is this? And that does follow from all the calculations that we did. And it's kind of a mixture of, what we computed explicitly and what we can sort of deduce from the functional equations at this point. Yeah. Right, but you can, thanks. I mean, there's a principled way to solve these functional equations, which was also in the paper. The paper is, there are different chunks doing different parts of the work, so I'm not going to go through all of it. But oh yeah, Yeah, so I mean, the way we check something like this, so once you have the kernel, you want to show that this is greater than or equal to 0. And the thing you have to do is, the way we did it is transform everything. So this has, j's. It has, essentially, yeah, I mean, it has all these functions. It'll have j, of tau and z. It'll have e2 of tau, e2 of z. It'll have log lambda, et cetera, et cetera. So everything we converted first, basically using classical sort of elliptic identities to functions of lambda of tau and lambda of z. So let's call them x and y. Okay, so lambda of tau and lambda of z, because tau and z lie on the imaginary axis, so lambda goes between 0 and 1. And so now you're on the unit sphere, unit square, and everything is, a function of, you want to show that there is some function. I mean, you can compute what the inequality it gives. It's some polynomial, but there are some terms which involve Jacobi elliptic functions, E and K, which show up, and there are some logs which show up. So there's some horrible mess. You have to show that that's positive. And then a lot of that we did by breaking it up into subregions and doing interval arithmetic. You can see there are some regions where it's clearly going to be positive. You can either do sort of by hand, you can say, mean value theorem or something. But interval arithmetic is a principled way to do it. So most of the time we plugged in, we did it by so either interval arithmetic or power series expansions. That's the other thing that we use. So if you have a reasonable power series expansion, you go up high enough, then you can say, here's your main term. It's polynomial. You can check that it's bounded, and then you have some remainder which is small enough. So yeah, I mean, this requires a tremendous amount of sort of calculation. At this point, I think at this point, the 8-dimensional calculation, so it's checked in both Mathematica. I mean, 8 and 24 are sort of all set up in Mathematica, but it takes maybe a month or something. I've converted, Saindri and I mean, some of us have converted at least the 8-dimensional thing to Sage, and it runs, I think, in, I believe, less than an hour. So it's pretty quick. And 24 dimensions, we hope we haven't converted everything, but hopefully it'll be, a few hours or something. It'll be reasonably quick, and then we can sort of declare victory. So yeah, but it would be nice to have sort of, more. I mean, we for a long time we thought that there must be some more elegant proof involving, some kind of sum over the group, SL2Z or something, like the way you compute Eisenstein series. Maybe there's some kind of, function that you have to sort of sum over translates of the group, and then that gives you some positivity. But we couldn't come up with something nice. Anyway, if you feel like thinking about that, that would be great. Right, thanks. Yeah, that sounds good.